Okay, this is a review video for quantum numbers. Kind of should put it all together with maybe a couple of details that you might have missed before. Anyways, quantum numbers come from quantum mechanics, and quantum mechanics tell us that the fundamental property of any quantum system is the wave function. It's got this funny Greek symbol psi. All properties derive from the wave function. And this was figured out by Erwin Schrödinger. He derived a famous wave equation relating the energy of the quantum system with the wave function. And I'm going to show it to you now. No, I'm just kidding. I'm not going to show it to you. The math isn't important. I will say that the square of the absolute value of the wave function like that is significant because that defines the probability of finding the electron associated with a given wave function, which we'll talk about in a minute. You solve for the wave function to find the quantum states representing the electrons in atoms. These are the things that that Bohr first figured out with his Bohr model, and he only realized that there was one quantum number n. But as we find out, these solutions are actually three-dimensional orbitals that need three quantum numbers to describe. So they are n, l, and m sub l, which we've already covered. I'll review them real fast right here. The principal quantum number n indexes the size and energies of an orbitals in a shell. So with a given n value, we talk about a shell. It takes values starting at 1 and going up as high as you need. We only need up to 7 to fill the periodic table, though, so that's usually where we stop. Each row of the periodic table starts with a higher value of n. So as you go down the rows from top to bottom on the periodic table, n is getting higher. The angular momentum quantum number L is the next one, and that indexes the shapes of the orbitals in the subshell. It takes values that start at 0, so it can always be 0 for any value of n, and then as n increases, more values are possible. So it goes all the way up to n minus 1, and there can be multiple values for a given n. If n equals 3, L could be 0, 1, or 2. We give letter codes to the different number values to distinguish the L quantum number from the N quantum number. And you've seen these before. L equals 0 is S for sphere, L equals 1 is P for peanut, L equals 2 is D. We jokingly said different, and L equals 3 is forget about it. Okay. The magnetic quantum number M sub L, this actually indexes the orientation of each individual orbital in space. It takes values that start at negative L and go through 0 all the way up to positive L. So there are 2 L plus 1 values for each L subshell. And we've already talked about this. There's 1 s orbital, there are 3 p orbitals, there are 5 d orbitals, and so on. And that all kind of fits together. Like I said, this is just a quick summary. Review it as many times as you need. And so each orbital has a distinct combination of n, l, and m sub l. Okay, so as we already said, each orbital represents a 3D shape in space. And the meaning of that shape is that it represents the region of space where you might find the electron associated with the 3 quantum numbers in question. Okay, and so if you have the simplest case where you just have n equals 1 and l equals 0, this gives the highest probability of finding the electron very close to the nucleus, and it decays to lower values as the distance away from the nucleus increases, and that describes a spherically shaped distribution of points. You'll remember that L equals 0 is S, and S is for sphere. This is Y. And so if we go through the math of all the other ones, which we're certainly not going to do, you get the other shapes associated with the higher values of L. We said L is for p orbitals. When L equals 1, that's a p orbital, and those are peanut shaped. They look like this. You can have one along the x-axis, you can have one along the y-axis, and you can have one along the z-axis. And if you add all 3 of them, you can see that they fill kind of a spherically shaped region of space when you consider all 3 at once. So there's one for each of the axes, and you have the 3 quantum numbers. Those are related. And then just as with anything, when n goes up, the p orbitals get bigger. So a 2p orbital is bigger than a 3p orbital is bigger than a 2p orbital, and so on and so forth. L equals 2. Now, we haven't seen these before. I'm going to go through them really quick. D orbitals are different, right? They have more complicated shapes. Okay, we're not going to go into any more. I just wanted to give you a chance to look at them once. There are 5 of them associated with the 5 possible values of the m sub L quantum number, and just with anything else, as n goes up, the d orbitals get bigger. The f orbitals, F was for forget about it. We're not going to worry at all about what these things look like, but just in case you're curious, they get very, very complicated as we go up higher to L values. These are 7 f orbitals, 1 for each possible value of m sub L when L equals 3, and as n increases, the f orbitals get larger. Okay, so we've now talked about the atomic orbitals describing the probability distributions of electrons around the nucleus, but you might wonder why we need such a complicated scheme. Why can't you just keep putting electrons in the lowest energy orbital? Why can there only be 2 electrons in each orbital? Well, physics tells us that electrons are antisocial and they avoid each other as much as possible. So this is what is known as the Pauli exclusion principle, which I alluded to many times in class, and basically it says no 2 electrons in an atom can be described by the same set of quantum numbers. So you might think that 1 electron goes in each orbital. Not quite. We've already know the answer for this. There's a 4th quantum number, m sub s, which indexes the spin. Spin is just a word that we use to convey that electrons have intrinsic angular momentum. There's a property of them that essentially can take 2 values, which we call up and down, or plus 1/2 and minus 1/2 when we're using numbers. Basically, the 2 different values of m sub s means that each atomic orbital can hold 2 electrons, 1 up and 1 down, like we're already used to showing in the electron orbital diagrams that you've been using. Okay, so one last comment I'm going to make before I go, I'm going to talk more about spin and how we know what spin is, how it was discovered at the end of this talk. You don't need to know that, so I moved those slides to the end for those who are interested and want to keep listening. The required stuff is that you know this, and then also one thing I didn't really talk too much about in class is that in a hydrogen atom, n really does index the energy. All orbitals with a given value of n have the same energy, but there's only ever 1 electron in a hydrogen atom. When you have multi-electron atoms and you're populating multiple electrons into each orbital, the energies split not just by n but also by L. And that's what gives rise to the pattern, the filling pattern that's on the yellow sheets in the classroom and that you guys have gotten used to using when you write electron configurations for atoms, and which you've seen sort of now how it's built into the structure of the periodic table in this unit. Okay, that concludes this review of quantum numbers, except for the part about the origin of spin and how it was discovered. Okay, for those of you who are still interested and still watching, I just wanted to briefly describe a very historic and famous experiment that's related to how we know that electrons have intrinsic angular momentum, or spin. And so this is called the Stern-Gerlach experiment. And briefly, what these guys did was they just passed a beam of atoms through a magnetic field. And the magnetic field has a special shape so that if the atoms passing through it are magnetic, they should be deflected. Some of them should be deflected up, some should be deflected down. Now, the classical prediction for the results of this experiment was that there would be a continuous distribution, right? Because if you think about a magnetic field in space, it's always going to point in a direction. And if you've just got a bunch of atoms that are tumbling as they fly through a vacuum chamber and pass through this field, at the moment they pass through the field, that orientation of that vector could be anywhere in space. And so basically what that means is that you would expect some of them to be deflected a little bit up, some of them to be deflected a lot up, and you'd have a nice, smooth, continuous distribution. On the other hand, quantum mechanics predicts that the orientation in space can only take certain values. These are the m sub s values. It can only be up or down for this unpaired electron. So what you need to do is choose an atom that has an unpaired electron, just one, and pass it through this specially shaped magnetic field, and that's what they did. What they did was they passed a beam of silver atoms through this specially shaped magnetic field, and silver has one unpaired electron. And what happens is that if it's quantum, you would see two bands. You would see one going up and one going down. And if it were classical, you would see sort of a generic blob distributed between the limits of these two spots. And so when they did the experiment, you can see on the left-hand panel, this is a very famous postcard that Stern and Gerlach sent to Niels Bohr, and basically it shows on this side with the field off, and when they turn the field on, it split into these two clear bands. And the important part of this picture is actually the hole in the middle. Classical physics predicted that the maximum of the distribution, so the darkest spot, should have been in the middle, and in fact quantum mechanics predicts there should be a hole in the middle, and that's exactly what Stern and Gerlach saw. And so this is postcards in German, but it says congratulations to Niels Bohr on the experimental verification of his theory. So it's a really, really cool example of some history associated with quantum mechanics. And there's a really nice anecdote. When Stern was given the Nobel Prize for this discovery, he said in his acceptance speech, I never would have got the Nobel Prize if I hadn't smoked cheap cigars. And the story is that they didn't think these experiments were working because the amount of silver that was being deposited on the glass plates they were using to catch the atoms was so small that you couldn't see it. And so they thought these experiments were failing and they didn't know how to interpret them. And so, like most professors, Otto Stern's office was kind of a mess, and he had piles of stuff, and he had the piles of the silver plate, the plates stacked up in his office where he smoked cigars. It was a different time. The cigars were cheap, and they had a lot of sulfur in the smoke. And over time, the sulfur in the smoke reacted with the silver, and it turned it into silver sulfide, which you could see. So it sort of developed the plates, and he could see the patterns that eventually led to this discovery and led to him winning the Nobel Prize. So anyways, it's just a fun story that goes along with one of my favorite experiments in all of atomic physics. Okay, I hope you enjoyed it. If you stuck around to listen, thanks.